Hello students, this is the second video on the chapter Solutions. Hope you all have seen my previous video. In the previous video, we already have discussed the classification as well as the different concentration units to express the concentration of the solutions. In that video, we already have seen a few problems based on concentration units, but yet we require a little more practice on that particular topic. So let's begin this video by doing a few problems from our concentration unit. The very first problem is there for you. Calculate the mole fraction of ethylene glycol in a solution containing 20% of ethylene glycol by mass. 20% of ethylene glycol contains 20 gram of solute and 80 gram of solvent. The mole fraction of ethylene glycol is given as number of moles of ethylene glycol divided by total number of moles of ethylene glycol and the number of moles of water. Number of moles of ethylene glycol is calculated as given here. We use the equation given mass by molar mass. So the equation comes out as 20 by 62 and you get the value as 0.322. Similarly, we calculate the number of moles of water given mass by molar mass, that is 80 by 18, and the value is 4.44. On substitution to the mole fraction equation of ethylene glycol, we'll get the value as 0.0676. Now, if you are supposed to calculate the mole fraction of water, we can use the concept that the total mole fraction of the components in a solution is always equal to 1. So, using the equation, the mole fraction of water comes out to be as given here. The second problem. Calculate the molarity of a solution containing 5 gram of NaOH in 450 ml solution. This is a straight question. Directly take the equation of molarity as M is equal to Wb into 1000 by Mb into V. The given data are Wb is equal to 5 gram of the solute, Mb is equal to 40 gram per mole, that is the molecular mass of NaOH, and V is 450 ml. By substituting and solving, we will get the value as molarity is 0.277 mole per liter. The second problem is based on molality. Calculate molality of 2.5 gram of ethanoic acid in 75 gram of benzene. Directly taking the equation, M is equal to Wb into 1000 by Mb into Wa. So, getting the data from the question, Wb is equal to 2.5 grams, Wa is equal to 75 gram, that is the mass of the solute, and Mb is equal to 60 gram per mole, that is the molar mass of the solute. By substitution, we get the value as M is equal to 0.55 mole per kilogram. Hope you have all understood the problems being discussed here. Now let's move on to our today's topic. Today we are going to discuss about solubility. Solubility and the factors which is going to affect the solubility. Solubility is actually the ability of a solute to dissolve in a given solvent. Now that depends upon the nature of the solute, the solvent, the pressure which is present there and the temperature which is maintained there. Based on the nature of the solute and solvent, we can see that we have got a code word given there. Like dissolves in like. That is, when we consider the nature of the solute can be either polar solute or a non-polar solute. Similarly, when the solvent is considered, we have them as polar solvents and non-polar solvents. As far as solubility of the substance is considered, a polar solute dissolves in a polar solvent. Similarly, a non-polar solute dissolves in a non-polar solvent. We can see few examples here. NaCl, as you already know, is an ionic solid and it is a polar solute. It dissolves in the polar solvent water. A non-polar solute solvent example is naphthalene being dissolved in benzene. So, do remember the code word for the nature of solute and solvent. Like dissolves in like. So, after finishing the first concept, that is the nature of the solute and solvent, let's move on to our next section. Let's discuss the second condition, that is effect of temperature. Here we are considering a solid solute being dissolved into the solvent. When we take a solid solute, we can see that first an energy is consumed to break the bonds of the solute. Then an energy is released when the bonds is being formed with the solvent. You can see here how the bond is breaking and then how the bonds is being made with the solvent particle. When we compare the energies required to break the bond and the energy being released, when the two quantities is compared, if the energy required to break the bond is less than the energy required or released when the new bond is being formed between the solute and the solvent, such a process is called as an exothermic reaction. Now, we have learnt in our 11th standard Le-Chatelier's principle. When we apply Le-Chatelier's principle onto an exothermic reaction, we know that an increase of temperature never favors the reaction. So, that is why in an exothermic reaction, an increase of temperature is not favorable. Hence, when we consider the sum total of such a dissolution, we can see that when the solute dissolves into the respective solvent, we feel a amount of heat energy coming out of the system, or we easily understand that this dissolution is an exothermic reaction and an increase of temperature doesn't favor the condition. When we consider the graphical study of certain examples like cerium sulfate or sodium carbonate, you can rightly see into the graph here that as the temperature is going to increase, the solubility keeps on decreasing. The two graphs has been plotted for you here. Cerium sulfate, as temperature increases, solubility decreases because it's an exothermic dissolution. Similarly is the case for sodium carbonate also. On the contradictory, we may have a condition coming to us where the energy which is required to break the bonds of the solute is much higher than the energy released when the solute forms a bond with the solvent. Such a case we call it as an endothermic reaction. That is, when we come across such sorts of dissolution, we feel a cold atmosphere around it, or we feel a cooling condition onto the solution system. Again, here also we can apply our Le-Chatelier's principle, which states that for an endothermic reaction, an increase of temperature always favors the reaction condition. That means an endothermic dissolution will be favored by an increase of temperature. This particular condition of an endothermic reaction can also be expressed in terms of certain examples in a graphical method. You can see in the graph, we are going to consider two types of examples there. The first example is that of sodium nitrate. You can see that sodium nitrate on dissolution, excessively the solubility increases with increase of temperature. Same way, we have got potassium nitrate onto the graph and we do have NaCl also on the graph. So, these are the examples which shows that they are endothermic and their solubility increases with temperature. Sodium nitrates, this dissolution property is used in cold packs. We have already seen the usage of these cold packs for particularly the sports persons who undergo certain injuries. For them, immediately a cold pack is given, because when the cold pack is given, since ammonium nitrate is filled into the cold pack, it easily dissolves on a small shaking, and the endothermic dissolution causes the pack to become cold. Now, moving on to the third effect, that is the effect of pressure. When we discuss about pressure, it is seen that pressure does not have any significant effect on solubility of solids in liquids. It is because the solids and liquids are highly incompressible and practically remain unaffected by changes in pressure. So that means when we consider our solution nature as gas in liquid, of course we have to discuss the effect of pressure in detail. Now let's take the example of a gas in a liquid. You can see here that we have got two containers given there. The first container with the P1 pressure and the second container P2, that is a higher pressure. When the pressure is increased in the second container, you can see that the number of particles of the gas dissolving into the solution has increased. So we can conclude the solubility of a gas increases with increase of pressure. Do remember, students, that this is a condition of the nature of solution as gas in a liquid. Now, this effect of pressure on solubility was explained by William Henry. He quantitatively expressed the effect of the partial pressure of the gas being dissolved to its solubility into the liquid. Henry's law states that at a given temperature, the partial pressure of the gas in a vapor phase is directly proportional to the solubility of the gas in the solution, and this is expressed as partial pressure of gas is equal to Kh, where Kh is the Henry's constant, into the solubility of gas, which is expressed here in terms of mole fraction. Now, when we consider the Henry's constant, you can see here that we are not giving you any constant value. This is because Henry's constant is constant for a particular type of the gas and the particular type of the temperature at which it is measured. You can easily see here in the table. Now you can see here a tabular column where the gases, their temperature and the Henry's constant which is being measured is given. Let's concentrate on to the two examples of the gas, nitrogen as well as oxygen. You can see here that the nitrogen at 293 Kelvin has got a Henry's constant of 76.48 and that at 303 degree is 88.84. That confirms that Henry's constant depends on the nature of the gas and the temperature. Now comparing the values, you can see that as the temperature increases, similarly the Henry's constant is also increasing. As temperature increases, Henry's constant is also increasing. So by the Henry's law, we can easily conclude that when temperature increases, solubility decreases. We would have fancied by our discussion so far that how do fishes survive in cold water? It is a very easy concept. Just now by Henry's law we understood that as temperature decreases, the solubility can increase. So the amount of oxygen in a colder region increases. Now we'll discuss the application of Henry's law. You can see here a figure where a glass of an aerated drink has been given with bubbles of gas being present there. The gas is being dissolved into the aerated drinks by applying a high pressure, and we do close the cork tightly to maintain that pressure. We would have all observed this, and whenever we try to open the sealed bottle, the pressure dips off and all the gas which is present there fizzes out of the bottle. So this is another application of Henry's law, which states that as pressure increases, or which gives a conclusion that when pressure is increased, more amount of solute can be dissolved into the given liquid. Now here you can see a person going into a deep sea. We call them as scuba divers. Scuba diver always carries a cylinder for the supply of oxygen, because when we go deep down into the ocean, the pressure is very high. When the scuba diver is under a high pressure, the dissolved nitrogen, the nitrogen present in his cylinder along with the oxygen, gets dissolved into his blood system. But when the scuba diver comes up to the surface at a very fast rate, at that time the nitrogen oozes out of the blood or gets undissolved from the blood and forms bubbles, which causes a capillary block that you would have seen there. So nowadays, an alternative which has been suggested is that we have reduced the amount of nitrogen there and then we have mixed helium there. Now, why the mixing of helium? A helium is found to be a less soluble type of a gas, almost 5 times less soluble than nitrogen. So, of course, when the dissolved gas is lesser in amount, when the scuba diver comes up to the surface, then the coming out bubbles of the dissolved gas also decreases. So, hence, we can just go through the concept one more time here. Scuba divers come towards the surface. The pressure gradually decreases. This releases the dissolved gases and leads to the formation of bubbles of nitrogen in the blood. This blocks capillary and creates a medical condition which is known as bends. And this is a very painful and a dangerous condition to life. Of course, we have already reached to an alternative there. Just add on more amount of helium than nitrogen so that it is less solid. Going on to the final application of Henry's law, you can see here a mountaineer climbing onto a very high altitude. They too carry oxygen cylinders. Now, why they carry oxygen cylinders? Because as you move to higher altitudes, there is depression in pressure, or we have low pressure region. Low pressure means low concentration of oxygen. So often these climbers suffer a requirement of oxygen, and this low level of oxygen makes them weak and they have a condition of unable of clear thinking, and that symptom is called as anoxia. Let's do a problem based on the Henry's law, which will be the last of the session. Calculate the solubility of oxygen in water at a temperature of 293 Kelvin. When the partial pressure exerted by oxygen is 1 bar. Henry's constant for the oxygen at 293 Kelvin is already provided there. So you can simply do the problem by taking the direct equation as Henry's law, P is equal to Kh into mole fraction. Substituting the given quantities, we can easily get the solubility as given there. That was the last concept we discussed here. So now we can see that in this session, the part 2 of the video, we have discussed the concept of solubility and how the solubility depends upon the nature of the solute and solvent, the effect of pressure, the effect of temperature. When the particular solute changes from solids or liquids to a gaseous system, then the effect of temperature and pressure becomes rather important, and we came across the concept of Henry's law. Henry's law and its application in our day-to-day life was also discussed here. So, that is all the concepts summarized into this video. In our next video, we will move on to the concepts related to a liquid into liquid binary solution. So, hope all the concepts are well clear for you. Thank you. That's all for the video.